the cryptanalysis. So, but it's security this of the multivariate schemes. This is mainly, as I say, try to describe as precise as possible the resistance of the system, and also how we can broke it. All right, all this, as I say, in the public key cryptography, once you have a map, you describe it, and you have that is injected or subjective. You know that there is a way to invert, but this way to invert can be difficult, and this is what we have to address. And also, I mean, you know also that there is a second way to invert, that this is the secret key. Okay, so for us, as you may guess, the main ingredient is study with Grosvenor basis. Grosvenor basis, let's say, attack. Well, we'll call it attack, but not only is attack, right? In fact, we will talk about how to say, in the Grosvenor basis, complexity of Grosvenor basis of Grosvenor basis computation, Grosvenor basis computation, and we will just see this in the example of a scheme that I give yesterday, and the other scheme they will see. Okay, that's the all right. So but there is also other kind of attacks. We will see. First one is Grosvenor basis. Then we have also linearization. The linearization attack. We'll have a sample of these attacks, and also mean rank. Mean rank, I will explain, as the title say, mean rank attack using the mean rank problem. Okay, and then I will give you a very good reference for this. Is there is a note of a course of a mini course of Elisa Gorla. You can find it on the internet. Wait a minute. Let's see. I have it. Wait a minute, where is? I don't find the reference. Well, it's something like complexity of Grosvenor base computation. An application to cryptography. Crypto. Okay, so this is a very, you can find it on the internet, and also I can send to you. It's a very, very nice course about the subject. Okay, okay. Then I will start to see all these all these attacks. Starting with the example I give you is remember the MI scheme. IMI maximum to IMI scheme. Okay. In this case, we have remember case a power of a prime. Let me see. And we have, I will remember, we have, I don't put the whole schema I do not repeat, but the central map is f of z is set to the q to the I plus 1, okay? And then this, after applying the isomorphic phi and the linear T and S, the linear isomorphic, we get a polynomial P of x equal P1 Pm in general, or Pn, sorry, that they are quadratic. Remember that, of course, we can use Grotner basis. Grotner basis to invert directly, say directly the map, no? So the map P. So that means that we have y equal to y1, yn, okay, belonging to f q to n, and we have to find pi minus 1 of y, okay? And then we have to solve, that means is p1 of x equal to y1, etc., Pn of x equal to yn. All right? And then this is equivalent, to solve this, is consider the ideal P1 of x minus y1, etc., Pn of x minus yn. All right? And we have to, and then Grotner basis can, if there is a finite number of solution, a finite number of solution over the a Grotner basis can find it. Grotner basis, let's say a Grotner basis computation can find it. So you see here the main application of the Grotner basis. Okay, so in fact we have the so-called same lemma that gives really the solution. Okay, so we have wait a minute, I found it, the same lemma. So theorem is called the same lemma. So the next thing, take the legs, take g of xn with the legs monomial order or term order. Okay, in the first day, you explain how is this, how it works. Okay, and then and consider the ideal that we have, and consider the ideal we were there. We call it y. Okay, y. Okay, I will not write again. And y. Then assume that, as I say, I has a finite number of solution has a finite number of solution solution. Let's say alpha, and for any solution, any solution, alpha. The beta, we have alpha n is different than beta n. So we can always, in principle, find some change of coordinates in such a way that all the solution has the last coordinate different. Okay? Then, if also we need the ideal is radical, then the Grobner basis of y is S1 minus H1 of x and x m minus 1 minus x m minus 1 of x n xn and then hn of xn, okay, and degree of hn is the number of solution of okay. So really, we have Grobner basis. Explained you the other day, allow us to eliminate the variables, okay? And if we have this, let's say, strong condition, then when we eliminate the variables, we get at the end, polynomial in one that geometrically means that in the space, we have a finite number of solutions, but then we will project over the last variable xn, then all of them will give difference, and okay, you see, even Grobner basis gives you the solution. Okay, so you see this is kind of miraculous. Well, I think we need another hypothesis. The base is reduced. Okay, all right. So you see. So now the question is what is the cost of doing that? And this is what we call the complexity of the Grobner basic computation. Okay. So as I say, this can always. What I say always. So we need what is the cost? The complexity. Okay, of the computation. So, because you know, we always, I will not repeat again, we always can do that, but how much cost? I mean, there are different measures of the cost of the cost, but the main one is what is cost, the solving degree. Solving degree of I is the maximal of the degrees of the Grobner basis computation using Macaulay matrices, like using, for instance, the algorithm F4 or of Fourier, for instance. Okay, so I will not be more precise. Just to have an idea. Just this is, I mean, at the end, you use this algorithm, you use reduction using using these matrices. If you know the maximum degree of the data pair, then using the complexity of the Gauss elimination, you can determine that. Okay. The problem, of course, is that this is always the same. The problem is that you have an ideal. We have several polynomials, and you have several polynomials with some fixed degree. But then the Grosvenor basis computation we start to make a computation, you know, it was explained here how to do it. But then, of course, the degree can grow. So it's not easy a priori. It's impossible a priori to say where you have to stop, what will be the maximum. So this is really the problem, okay? And in fact, this is, for instance, this is the problem in particular for the case of inverting the map. No? In fact, I will say, there has been a many conferences in cryptography, and they also people, multivariable cryptography, they always say, you know something about Grosvenor basis. Can you tell me how you compute the solving degree or last fault degree? There is other, and they are always very interested in that. I'm not an expert, but this is the main measure for the complexity. Okay, so that all right. Then I will. And in some cases, for instance, when we use Grosvenor basis for computer, for instance, the mean rank, I will talk about that. We can say something, but as I say, a priori, it's not easy to know where to stop. And we will see. So this is the general, theory, and we'll see that in practice with the cryptographic scheme that we were more interested. So we'll start with the Imai Matsumoto Imai. Remember Matsumoto Imai that we were yesterday. And in fact, in the case of Matsumoto Imai, it's a little special. We don't need Grosvenor basis is not the best way to try to lower, to broke it. Broke the system means lower the expected complexity. So there are, but in any case, this is interesting. I will explain why. Okay. So remember you have the central function is FQ, FQN, and FQN. All right. F of Z is Z Q I plus 1. Okay. And remember that this is, we need that because they give the polynomial, the corresponding polynomial, that is the composition with the linear pair, is quadratic. Is quadratic. In this case, as I say, in fact, it was broken, so this was invented in 1988, and it was broken 1996 by Patahand. It's a French. I think was really the one who really started the serious work about multivariable cryptography. So now we, and in fact, use a very clever idea that in fact, it's interesting to see it because you see this was resisted for 8 years, but at the end, they can work in a very simple way. Okay, I will explain that. So this is very specific to this system. Is that? But I will explain. So how it works? So here at the level of the big field, we have, we call y, we have that, no? The image plus 1 equal to y. Okay, this is the map. Okay, and then we can just elevate this both sides to qi minus 1. So we get z qi plus 1, qi minus 1, qi minus 1. Okay, and this, you know well, this is z, we put here, you multiply this is z to qi squared, so q2i minus 1 equal to y qi minus 1. And then we can pass, we multiply pass the y in the denominator there, and the z and the y denominator in the denominator there. I mean, multiply, that is, multiply by z and multiply by I, and then in both sides. So we get exactly z q 2i times y is equal to y qi times z. Okay, so we have an implicit equation in between the message and the message and the cipher message. Okay, and this is really very bad. So this is a fatal coincidence, really, and we should never have something like that. And with that, it is possible to break the system totally. I mean, you have one to find in an easy way the preimage. And this is an example of what we say that we call linearization. Linearization attack. Okay, why? Because this is, we have this equation to the level of the big field, but we apply the isomorphism. I didn't write it, you can see the note of yesterday. We can pass this equation to the small field, fq to the n. Okay, fq, sorry, all right? Fq to the n, all right? And then we will have some quadratic equation, and equation in the down. Okay, so in this case we have the coordinate as 1xn for z, and we will call y1 yn for y. And remember, because when I explained the other day, when we have a power of q, when we express this down, we have this is linear. Okay, so this is linear, this is linear, and this is linear. So that means that we have now is a family of equations that are of degree 2. So this, but at the degree 2, but they are linear in this group of variables. So we will have a family equation alpha yj xy xj yj is equal to 0. Okay, and in principle, because we have because of the h of the t, we don't know what are these coefficients, all right? But now we can, but we know that this equation exists, okay? But now we use, I don't know if I write here, what is called chosen text attack. Chosen text attacks is attack. So this attack means that we have the encryption machine. Encryption machine is the map P. Then we can build pairs of any number of pairs of chosen text and the corresponding ciphertext. So we choose. So we take many many pairs, x, and then p of x is y. P of x, remember, because this is y. Okay, and then we have a lot of pairs and then we can think, of course, in this equation we know anything, but if we have a lot of pairs, we can think in this equation as linear equation. We know this x and y, and then it's a linear equation in alpha.